So this is lesson 2 in impulse and momentum, and this is about conservation of momentum in 1 dimension and in 2 dimensions. If you haven't watched lesson 1, which defines what momentum is and how to change an object's momentum through an impulse, go back and watch lesson 1 before you move on to this lesson 2, conservation of momentum. So, conservation of momentum comes from the idea that when there's a collision between 2 objects or an explosion that separates 2 objects, there's a force felt equally by each object, or an impulse, a force over a period of time felt equally by each object. So each object is going to experience that force, and each one will have a change in momentum that's equal and opposite. So together, the whole system has no change in momentum. So in a closed system, the total momentum is always conserved. Always conserved. So we can write that out. We wrote EO equals EF for conservation of energy. We could write that out with the sum of the momentum in the system initially is equal to the sum of each object's momentum in the system after the collision. And I recommend drawing pictures as a strategy for working through these problems, because then it's pretty easy to see that the sum of the object's momentum is the momentum of each object added together before the collision. And we can set that equal to the momentum of each object added together after the collision. So momentum is mass times velocity. It's a vector, so if the velocities are in opposite directions, just remember we need to call one of them negative, which we usually call to the left negative. So it's just MA VA initial plus MB VB initial equals MA VA final plus MB VB final. So some students are like, do I need to memorize this equation? You don't need to memorize it because it's really conservation of momentum, and then in your reference table, it shows that each object's momentum is mv. So if you just keep track of everything and label everything correctly, it'll work out. So we can look at this collision between a cart with a mass twice the mass of the other cart. That second cart was at rest. The first cart was moving. We can see that in the collision, this object's momentum, the 2 mass objects' momentum changed, and the 1 mass object's momentum changed. And we can calculate that if we want to. So let's take a look. So if we calculate the momentum of the 2m object, we would just take its mass, 2m, and multiply it by its speed, which they found to be, from the slope of this position versus time graph, 40.9 centimeters per second. So we could express the momentum as 81.8 times an unknown mass, kilograms times centimeters per second. And then after the system, after the collision, they both have momentum, so we have to calculate both of them, and we have to add them together. They're both moving in the same direction, so we don't have to worry about negatives. So the single mass object had a speed of 52.8 centimeters per second after the collision, and the 2 mass object had a speed of 13.4 centimeters per second. So if we multiply 2 times 13.4, we get 26.8, and if we add that 52.8 to 26.8, we get 79.6 m. So before the collision, we had 81.8 m. After, we had 79.6 m. So we're pretty close to conservation of momentum there for an experimental setup. Notice these carts have magnets, repelling magnets facing each other. So there's this force, this impulse that each cart gets. There's a force that each cart experiences, but one experiences it one way and one experiences it the other way. So their momentum, their change in momentum would add to 0. And so the total momentum of the system is conserved. Kind of cool. There's 2 types of collisions or explosions or interactions we'll see. And we can think about this Newton's cradle as an example of an elastic collision. And whether some collision is elastic or not is just based on the question, is the kinetic energy conserved? So if kinetic energy is conserved, then yes, this is an elastic collision. If it's not conserved, then it's called inelastic. And that's the only way something is an inelastic collision, is if kinetic energy is not conserved. So with elastic collisions, then total momentum and kinetic energy is conserved. Momentum is always conserved, so really it's about whether kinetic energy is conserved. In an inelastic collision, only momentum is conserved, but kinetic energy is not conserved. The energy is transformed into other forms of energy, sound, heat, something like that. So most collisions that we're going to see are inelastic collisions. We live in a world full of friction. The only perfectly elastic collisions that I've heard of are ones on the molecular level. So collisions between molecules are considered elastic. Kinetic energy is conserved and momentum is conserved. But in your bumper car collisions and car crashes, in pretty much every collision that we're going to see, that kinetic energy isn't conserved. But the only way to know is to calculate kinetic energy before the collision and after the collision and see if they're the same. Perfectly inelastic collisions occur when objects stick together. And in that case, kinetic energy is also not conserved. So perfectly inelastic collision would be when the objects stick together and move together. An explosion is kind of like the reverse of that. So if you consider a cannon with a cannonball inside, there is a force that acts to accelerate the cannonball and the cannon, an impulse that changes the momentum of the cannonball and the cannon. Each feels that same impulse, but the cannonball ends up with a greater velocity because it's less massive, and the cannon itself goes backwards with a smaller velocity. So let's do an example. So we have a cart A with a mass of 0.5 kilogram moving to the right at 2 meters per second, and it hits cart B with a mass of 1 kilogram moving toward it, so to the left, at 3 meters per second. And car A rebounds, so it bounces back with a speed of 1.5 meter per second. What's the final speed of the collision? Or final speed of cart B? So I recommend drawing a picture, a before and after picture for every scenario. So I drew my cart A, I gave it its initial velocity. I drew my cart B, I pointed that arrow to the other way. So that tells me they're in opposite directions. I need to call one of these negative. And then after, we know cart A rebounds, so it goes backwards at 1.5 meters per second, and we want to know what speed cart B is moving with after the collision. So if you draw your picture, then it's a little easier to label what things are. So this is the velocity A had initially. This is the velocity B had initially. This is the velocity A had after the collision, so we'll call that negative because it's to the left, and we're looking for the velocity B had after the collision. So with this picture, we can then use our conservation of momentum equation with the idea that we're calculating the momentum of each object before. So a 0.5 kilogram times 3 meters per second is going to be 0.5 kilogram times 2 meters per second is going to be 1 kilogram times meter per second. Plus mb is 1 times vbo, which is 3. So it's to the left, so it's negative 3 kilograms times meters per second. And we'll set that equal to the momentum that A had after, which they gave us enough information to find that. The mass is 0.5 kilogram. The velocity after is 1.5 meters per second. So that would be a final momentum for cart A of negative 0.75 kilograms times meters per second. And then for cart B, we don't know the velocity, but we know the mass, so we'll plug that in. So we'll add these up. So 1 minus 3 is 2, and then is minus 2, and then we'll add our negative 0.75 over, so minus 2 plus 0.75 is minus 1.5. That equals 1 kilogram times the velocity B had finally. We makes it a little shaky. And that would leave the velocity V has in the end to be negative 1.25 meters per second. So that's an example of how to do a conservation momentum problem with a collision between two objects that don't stick together. If we wanted to figure out whether it was elastic or inelastic, what would we do? We would calculate the kinetic energy of the system before the collision and the kinetic energy of the system after the collision and compare those numbers and see if they were the same. Then it would be elastic, which is very rare, or if they're different, it would be inelastic. This is also true in two dimensions. So if we have two hockey pucks on an air hockey table, the moment they impact, each feels a force in the opposite direction. So each one is going to have an impulse. Each one is going to change its momentum, but they're going to change in completely opposite ways. So the total momentum of the system stays the same, and that's really convenient. So we can use that to analyze problems with two-dimensional motion instead of just a cart moving along a track. With two-dimensional motion, you would do sum of the momentum in the x direction initially equals the sum of the momentum in the x direction final, and also separately treat the y direction. Sum of the momentum in the y direction initial equals the sum of the momentum in the y direction final. And that's just because it's a vector, and the vectors have different components in the x and y direction. So on your homework set, I think I have pulled up here, on your homework set, there is a problem where, let's see, you have to do two-dimensional conservation momentum, and it's problem 28 here. So just treat x and y separate, and then there's a conceptual question. The first one has you think about two-dimensional conservation momentum. So if a firecracker splits into three pieces, one goes north, one goes east, what direction is the third one going to go in order to keep momentum conserved? So that would be opposite the two. So D. So this was lesson number 2 on conservation momentum. And let me know if you have questions.